Hello everyone. So in this segment, we're going to start a new topic. All right, we're going to learn a new data structure known as binary heap. So a binary heap is a tree-based data structure. All right. So a binary heap is a new data structure. This is also a tree-based, and a binary heap is also a binary tree. Okay. So we're going to learn about binary heap. We're going to see the properties of binary heap. And as we know that every data structure, we are going to implement that as an abstract data type. All right, so we're going to learn about the operations that we are going to implement as an operation of binary heap. So a binary heap is a tree-based data structure that is a complete binary tree and that follows heap property. All right. So here this binary tree, the binary heap is different from the term heap that we sometimes used in dynamic memory allocation. So we know that in dynamic memory allocation, whenever we allocate a memory, whenever we declare a variable dynamically, for example, like using new operator, all right, say new b, all right. So when we declare a variable dynamically, so dynamically means during the runtime, this variable actually allocates a memory space in our memory. Okay, so during this allocation, they actually allocates a memory space from a data structure known as heap. All right. Now this binary heap is actually different from this heap. All right. Just to let you know, because so when you are going to learn about the memory allocation, you may have heard about this data structure, all right, in operating system also, but the heap used in dynamic memory allocation is different than this binary heap. All right. Now binary heap has two properties: structure property, ordering property. So structure property is a binary heap, is a binary tree, and this is a complete binary tree. Now, if a binary tree is a complete binary tree, we can represent that binary tree as an array very easily. All right, so we're going to also learn about that, how we can represent a complete binary tree using an array. All right, and in this binary tree discussion, means in this binary heap discussion, a binary heap is a binary tree. All right, complete binary tree, but with some additional heap property. All right. Now, again, I'm saying that it is a binary tree, not a binary search tree. Okay. So the purpose of binary heap is different than binary search tree. All right. Both are binary tree, but binary heap has different properties than binary search tree. All right. Now, binary heap is a complete binary tree. All right. So what is a complete binary tree? A complete binary tree is a tree that is completely filled in every level. Okay. Only the exception can be at the bottom level. All right. So in the bottom level, we are going to add new nodes. All right. From left to right. So let's see an example. Let's see, we have couple of numbers here: 3, 2, 4, 7, 8. So I am repeating that again. A binary tree, a binary heap is a binary tree, but not binary search tree. All right. And a binary tree is a, I'm sorry. So a binary heap is a complete binary tree. Now this is an example of a complete binary tree. All right. So a complete binary tree means a binary tree will be filled. Right. Complete binary tree is completely filled at every level. Okay. Say for example, like this is level 0. All right. So we can have only one node. So in level 1, we can have at most 2 node. Okay. So this is our level 0. So at the level 1, we can have at most 2 node, right? So we're going to add 2 node here. So at the level 2, we can have how many node? We can have 2 to the power 2, 4 node. All right, so this both of these node 2 and 4, they can have at most 2 children. So at the level 2 we can have total at most 4 node. So let's add some more node here. So let's see, 7, 8, 9, 10. All right, so at the level 3 we can have at most 2 to the power 3, which is 8 node. Okay, simple, because here we have 4 node in the level 2. Each 4 node can have at most 2 children. So in the next level, means in level 3 we can have at most 8 nodes, right? All right, now let's see, we have only one more node, 11. Okay, all right, we are going to insert that. Now you can see that this is a complete binary tree. Here almost, I mean, every level is filled up with the at most number of nodes. Okay, now when I mean, the only exception can be at the bottom level. Okay, so at the bottom level is going to be filled up with left to right. So I have one node, let's say I have one additional node, 11. I'm going to add this node as the leftmost node. So if I have one more node, I'm going to add that as the right child of this node. Another node, I'm going to add it here. All right, so another node, I'm going to add it here. All right, so the only exception can be at the bottom level, but at the bottom level we're going to add every node from the left to right. Okay, so this is an example of complete binary tree. All right, so heap has two properties, structure and ordering. So the structure property says that binary heap is a complete, so binary heap is a complete binary tree. All right, now the next property is an ordering property. All right, so ordering property says that in heap we can have two type of heap. One is mean heap, another heap, another type of heap is max heap. Okay, so in a mean heap, for every node x with parent p, the key in p is going to be smaller than or equal to the key in x. All right, so for every node x with parent p, all right, say parent value is p and p has two child, x1 and x2. All right, p has two children, x1 and x2. Now the key of p will be smaller than or equal to the key in x. Okay, and that will be true for every node in this heap. So in the mean heap, the value of node, the value of the parent node, okay, the value of the parent node is going to be smaller than both of its children node. All right, so let's see the example here. Let's check every node in this data structure. All right, so you can see that for this node 1 has two children, 2 and 3, and 1 is smaller than both 2 and 3, right? So 2 is smaller than both 17 and 18, sorry, 19. 3 is smaller than both 36 and 7. So the value of the parent can be smaller or equal to the both of its children node. Okay, so here we have 17. 17 is less than both 25 and 100. Okay, so from this tree you can see that first we are going to check whether it is a complete binary tree. So it is a complete binary tree. Okay, so here we have one node, here we have two node, four node. Only in the bottom level we have two node, but they are filled from left to right. So this is a complete binary tree, and from the order property we can say that this is a mean heap. All right, because every parent node's value is less than its both of its child nodes value. So the value can be less than or equal to its child nodes value. Okay, now in max heap, okay, so in max heap, every parent's node value will be greater than or equal to both of its children nodes value. So if you have a parent node here and it has two children, x1 and x2, okay, the value of p will be greater than or equal to x1, and value of p will be greater than or equal to x2. All right, so let's see here. Here we have 100. 100 is greater than 19 and 36. 19 is greater than 17 and 3. 36 is greater than both 25 and 1. 17 is greater than both 2 and 7. All right, so these are the two properties of binary heap. So binary heap has to be a complete binary tree, and it has to follow the ordering heap property. So in the ordering property, there can be two different types, mean heap or max heap. Okay, so in mean heap, the value of parent can be less than, value of parent is going to be less than or equal to both of its children node. Okay, all right, so this is the property of mean heap property, and this is the property of max heap property. All right, all right, now let's look at some of the properties of a complete binary tree, because binary heap is a complete binary tree. So some of the properties of complete binary tree, we can actually use that as a property of heap also. Okay, and this is going to help us for it for the implementation of our heap data structure. All right, so we know that a complete binary tree is a binary tree. All right, so in every level will be completely filled. Only the exception is the bottom level. Okay, and we are going to fill the bottom level from left to right. Now, if we have a binary tree of height h, okay, we can actually determine how many nodes there can be in the complete binary tree with height h. Okay, and the number of node is going to be between 2 to the power h2, 2 to the power h plus 1 minus 1. All right, so let's see some example. Let's see, we have a binary tree with height 2. All right, so let's use height h3. All right, all right. So if we have a binary tree, complete binary tree with height h3, that is going to look like this. That height 1, 2. All right, all right. So this is our tree with height 2. Now we are saying that binary tree is with height h equal to 3. So with height 2, how many node we can have? All right, we can see that 1, 2, 3, 4, 5, 6, 7. All right, so which is exactly 2 to the power, the equation is actually 2 to the power 2 plus 1 minus 1. All right, so 2 to the power 3 minus 1, which is 7. Okay, so with height 2, all right, we can have at most 7 node. Now with height 3, how many node we can have? So if the height is 3, the minimum number of node can be like 7 plus 1, right? So we are adding only one node here, so that will make this tree with height 3. Okay, and we are only adding one node with this tree with height 2, so 7 plus 1. Okay, now this is our minimum number. Okay, and you can see that this is 2 to the power 3, means 2 to the power h. Now after this is completely filled, this is the same equation, the way we can find the maximum number of node with a tree in a height h. Okay, which is 2 to the power h plus 1 minus 1. Okay, so this 2 to the power h is coming from, like if we have a tree with h minus 1, all right, which is completely filled, so h minus 1 plus 1 minus 1. So this is the equation that you can have at most number of nodes with height h minus 1. Now when we are having a complete binary tree with height h, all right, we are going the minimum number of node is we are going to find by adding one node. Okay, so you can see that, which is All right, so minus 1, we are going to cut them, and here, all right, we are going to find 2 to the power h. All right, so this is the minimum number of node and this is the maximum number of node. So the height of a complete binary tree is going to be the log n, okay, and the floor function of log n. So a complete binary tree, we can implement that, all right, we can implement that as an array such that for any element in array position I, the left child will be in the position twice I, and the right child will be in the position twice I plus 1. Okay, and if we have the index of the child node, we can find the parent in the position of I divided by 2 floor function. All right,